And we are recording, my friends. Okay, so y'all, the last section in chapter 5 that we got this afternoon is called 5.4 Sampling Distributions and something called the Central Limit Theorem. Okay, so y'all, it says in this section we're going to talk about the relationship between a population mean and the means of samples taken from a population. Okay, so let's figure out what this means. It says a sampling distribution is the probability distribution of a sample statistic that is formed when sample sizes of size n are repeatedly taken from a population. The sampling distribution of a sample means is the probability of the distribution of the sample means. Okay, what does all that stuff mean? Okay, so y'all, let's look at this part right here, and I think this paragraph right here kind of is the easiest way to explain it. So look what it says, y'all. Consider the random variable x, the age of a student in the class. The age ranges of values may be from 18 to 36, and the population mean might be 27 with a standard deviation of 3 years. Now, if we took samples of 4 students and found their averages, those averages of the sample are going to have less of a deviation, as the spread will no longer be between 18 and 36. Okay, so let's think about that for a minute. If we found the ages of everybody in the class, Paolo, I remember the other day, 21. Since you told me December 98, you just 26, right? I can do mental math, right? Okay, so y'all, if we were to find all of our ages, right, and then we took the average, and then we found out what our standard deviation is, but then we said, look, let's take the ages of everybody in a single row. So Paula and Maya, right? Am I saying your name right? Mia. Mia. So Paula and Mia, we're going to find their average. Natalie, I'm sorry. We're going to take your average. We'll put you guys together. We're going to do you guys together. We're going to do your guys together. And we found those averages, right? Each of the averages of everybody in each row. Those averages, y'all, will have less of a deviation. Why? Because now we're looking at smaller groups, right? So the age compared to everybody, we might have a bigger spread, but if we look at just individual rows, the spread there of those averages will be more narrow. Okay, that's what the idea of samples is referring to. Okay, so y'all, there's something called the central limit theorem, and it says if samples of size 30 or bigger are drawn from any population with an average of mu and a standard deviation of sigma, then the sampling distribution of the sample means approximates a normal distribution, and the bigger the sample size, the better approximation. If the population itself is normally distributed, then the sampling distribution of the sample means is normally a distribution of any size sample n. It says in either case, the sampling distribution of sample means has a mean equal to the population mean. Okay, so what are they telling me? That the average is going to be the same as the population average, okay? So that number is not going to change. Y'all, the only reason that we talk about variance, and I know we don't really talk about variance a whole lot, but when we started in the beginning of the semester and we had like our data set, and I said, look, there's a way to find, when we find each of those differences, there's a way to find the average of those differences. And the first thing that we come up to is something called the variance. And then from the variance, we go to the standard deviation because we basically just take the square root. But what we're going to say is now, when we're dealing with sample means, okay, the standard deviation is going to be our regular standard deviation that we already had divided by the square root of n. That is the only difference that we're going to do that's going to change, y'all, in 5.4. And I'm going to show you, hey, how do I know when I need to do my standard deviation divided by the square root of n? I'm going to show you so that you always know, hey, do I need to divide by the square root of n or do I not? Okay. So let me scroll down here. Okay. And it says, just a very straightforward question, y'all. It says a population has a mean mu equal to 79 and a standard deviation of 21. Let's see if we can find the mean and the standard deviation of a, and right here, guys, this is what I'm going to use. Okay. A sampling distribution with a sample means of size n equals 49. Okay. So, y'all, one thing I want to mention is that my average for my sample means is going to be the same average that we had before. Okay. So, our average of our sample means is still going to be, y'all, 79. That number is never, ever, ever going to change. Okay. So, my population mean and the average of my sample means is going to be exactly the same. That won't change. What is going to change, though, y'all, is my standard deviation of my sample means. Sorry. What we're going to do here, y'all, is to find that standard deviation, we're going to take our previous standard deviation and we're going to divide it by the square root of n. Okay. So look, y'all, our previous standard deviation, they told us was 21. Okay. And we're now going to divide that by the size of our sample. And the size of our sample, y'all, it says right here, n is equal to 49. So I'm going to put a 49 right here. Okay, so look, y'all, if we take this is 21. Anybody know what's the square root of 49? 7, right? Guys, what's 21 divided by 7? 3. Okay, I'm going to ask you a question. Is my standard deviation of my sample means bigger or smaller than the original one that we had? Than our original standard deviation? Anybody know? What was our original standard deviation? 21, right? And what about the one that we got now? 3, right? So what does that tell me? My standard deviation of my sample means, y'all, is going to be a smaller number. Remember what we said? We said, look, if we took all of our averages or all of our ages and we found the average and we found the standard deviation, but then we found the averages of everybody in each row, those averages would be less different. They would have less of a change than everybody all together. Okay. That's what we're really saying here. Okay. Okay, so the reason why the first one stayed the same is because right here, my average of my sample means is going to be the same as my original average that I have. So that number, Mia, is never going to change. Okay, that number is never going to change. The only one that's going to change is my standard deviation. And I'm going to take my old standard deviation divided by the square root of my sample size. Okay. Excellent questions, y'all. Look, let me scroll down a little bit further. And let's see if we can figure out what's going on here. It says cell phone bills for residents of a city have a mean of 47. So y'all, I'm going to stop right there. My mean is 47, and it has a standard deviation of $9. So my standard deviation is 9. Okay. Now I'm going to start reading in the second part. It says random samples of 100 cell phone bills are drawn from this population, and the mean of each sample is determined. Find the mean and the standard deviation of the sampling distribution of the sample means. Okay, so look, y'all, what we're looking for here is both the mean and the standard deviation of our sample means. So y'all, again, one more reminder, y'all, my mean is going to stay exactly the same. That's still going to stay as 47, okay? But now let's see if we can find the standard deviation of our sample means. So y'all, what we're going to do is we're going to take our previous standard deviation and we're going to divide it by the square root of n. Okay. So look, we already know that our previous standard deviation, y'all, was 9. So I'm going to put a 9 here, divided by this of, sorry, let me get rid of my email, guys, because it'll keep dinging if I don't get rid of this. Boom, sorry. All right. So divided by the size or the square root of the size of my sample. So look, y'all, right here where it says random samples of 100 cell phone bills, that's just telling me that my n is 100. Okay. Okay. Question. Anybody know what the square root of 100 is? What times what gives you 100? Same number twice. 10, right? Good. Look, y'all, if you take your calculator and say, hey, what's 9 divided by 10? Boom, 0.9. 0.9. Now, y'all, what I'm going to do is I'm going to sketch a graph of my sample distribution, okay? What did we say our average was here? What was our average? Did it stay the same? Did it change? Stayed the same. And it was what? What was the average cell phone bill? $47, right? So look, y'all, that's $47, okay? Now, I'm going to kind of draw my picture here. Now, remember, y'all, where the curve kind of changes right here, this is going to be the distance between here and here is going to be my standard deviation, right? And we said our standard deviation, was 0.9, right? So look, let me do this. Let me kind of get this out of the way. Boom. It was 47. So look, y'all, if we added 0.9, wouldn't that number there be 47, 0.9? Or 0.9, I'm sorry, not 0.09, but 0.9, right? Because we're adding it. And if we wanted to subtract it, let's see, what's 47 minus 0.9? 46.1, okay? So look, y'all, what we're saying here, okay, if we think about this, let's look at the picture that we drew. Most of the cell phone bills have an average, or this sample has an average of $47. The first big group of them are going to be between $47 and $47.90. And this group over here is going to be between $46.10 and 47, right? Whereas, y'all, when we were looking before, remember our standard deviation was 9? So look, in the whole group, in the population, that first group was between $47 and $56, and this group was between $38 and $47. Do you see how that's a bigger spread compared to now when we're looking at our sample? In our sample, it's between $46.10 and 47, or between $47 and $47.90. Do you see how it's a much tighter group, right? That's what happens, y'all, when we start looking at samples. The samples have a smaller spread. They're not spread out as much, okay? They're not going to be spread out as much. All right. Y'all, we're going to do the same thing for the second problem. We're using the same information. The only thing that I'm changing here, my friends, the only thing that we're changing now is that instead of samples of size 100 like we did the first time, we're now going to do samples of size 64, okay? Let's see if we can find both our mean and standard deviation of the sampling distribution of sample means. So remember, y'all, originally our average was 47 and our standard deviation was 9, okay? So look, I'm just going to zoom back in here again, and I'm going to find my average of my sample means. Now remember, y'all, my average of my sample means is the same thing as the original average that we had, which was 47, okay? Now, our standard deviation is going to be our original standard deviation divided by the square root of n. And we said our original standard deviation, my friends, was 9. Now we're going to divide that by the square root of our sample size. And our sample size here, y'all, is 64, okay? Question, anybody know what the square root of 64 is? What do y'all think? What times what gives me 64? 8, right? 8 times 8 is 64. Look, y'all, I'm going to take my calculator. What's 9 divided by 8? 1.125. And guys, I'm going to go ahead and round it 2 decimal places because we're talking about money here, okay? Remember, we're talking about average cell phone bill. $47 originally in the population, 47 plus 9 more, 47 minus 9 more, right? Now, my average is still 47, but this number right here, y'all, wouldn't that be $48.13, right? And if we wanted to find the other number, we could take $47 minus 1.13, and this number right here, y'all, would be $45.87, right? And that's basically what we're looking at. So again, the bigger my size, the smaller our changes, right? The smaller our changes. Y'all, the next question I have, it's a similar question. What I'm trying to do with these first couple of problems, y'all, is just get us to understand how do we find the average of our sampling means and how do we find our standard deviation, okay? And then we'll actually apply this to something that like how can I use this or what is this used for? Okay. Y'all, let's take a look here. It says the braking distances from 60 miles an hour to a complete stop on dry pavement of an SUV are normally distributed with a mean of 154 feet. Okay, I'm going to stop right there, my friends. First thing I'm going to do, my average is 154 feet with a standard deviation of 5.2 feet. Okay, let's think about this for a little bit, y'all. Today's a pretty day, right? There's no rain in the forecast, nothing like that. You're driving, you're going back home, you're going to San Juan, you're going to Alamo, you're going to La Feria, wherever you happen to live, right? And you're driving, and all of a sudden, what's cuter to you guys, puppies or kittens? Puppies. All of a sudden, a puppy comes out in the road. You got to hit your brakes. You're going 60 miles an hour, right? Okay, so y'all, if you're driving an SUV, you're going to travel about 154 feet before you stop, right? That's what this is telling me. Plus or minus 5.12 feet, right? So you might stop at 159, or you might stop at 149 or 148 and change. You see what we're saying? That's really what the question is telling me here, okay? Now, what we want to do, it says, look, we're taking a look at samples of size 12, okay? So y'all, that's telling me that my N is 12. So if we took 12 SUVs, okay, and we found their average, how long does it take them to stop? What would that average be? It would still be 154 feet, okay? The average would still be 154. But if we wanted to know what would the standard deviation be, we're going to take our previous standard deviation, y'all. We're going to divide it by the square root of n, okay? So look, our previous standard deviation, 5.12 divided by the square root of 12. Now, let's do it like this. I'm going to go ahead and use this calculator, y'all, because I think it'll be a little easier. Let me clear all this business out. Y'all, I'm going to type in exactly what I see. Look, 5.12 divided by the square root of 12. Y'all, on my calculator, it did open up a parenthesis for me, so I'm going to go ahead and close that off. If it didn't, don't worry about it. And I'm going to hit equals. And y'all, if I were to go to 2 decimal places, what do you think? 1.47, 1.48? 1.48, right? Okay. So y'all, what are we saying here? Look, remember, my average is still 154. This number right here, y'all, would be 155.48. You're like, how'd you get that? Because we took 154 and we added 1.48 to it, right? And then we could take 154 and we could minus 1.48, and we would know that this number right here would be 152.52. So again, y'all, what are we saying now? If we took 12 SUVs, the average that it's gonna take for them to stop would still be 154 feet, but there would be less spread, right? It wouldn't be plus or minus 512, it'd be plus or minus 1.48 feet. That's all we're saying here. So I'm not really doing anything any different other than that one thing on how I find my standard deviation, okay? All right, so now how do we apply this? That's what the second part is, y'all. Okay, so it says probability and the central limit theorem. Okay, it says in previous sections, we talked about z-scores to find probability for individual members of a population with a normally distributed random variable x. In a similar manner, we can find the probability that a sample mean average x will lie within a given interval, okay? So, y'all, my formula on how we're going to do this is going to be very similar to what we did before, right? We would do x minus our average divided by our standard deviation. We're going to do the same process here, okay? So let's take a look and let's see if we can figure out how to do this question. Okay, so it says the population mean and standard deviation are given below. Find the required probability and determine whether that sample mean would be considered unusual. I'm going to talk to you guys about that unusual part in a second, okay? So look what it says. Find the probability that a sample mean is going to be less than 22.6. Okay, so look, y'all, we're going to say, what's the probability that my sample mean is less than 22.6? What we're going to do is we're going to convert this sample mean, my friends, to a z-score, okay? This formula right here, y'all, tells me how we're going to do that, okay? So first thing I'm going to do, we need to find our UX, or our average of our sample means. Y'all, the average of the sample means is the same thing as the average of the population mean, which is 23, okay? We need to find the standard deviation of our sample mean, okay? The standard deviation, y'all, is going to be our previous standard deviation divided by the square root of n, okay? So look, our previous standard deviation is a 1.17 divided by the square root of n. Y'all, take a look right here. We're looking at samples of size 65. So I'm going to call that a 65, okay? And just like we did previously, y'all, I'm going to take my calculator here. I'm going to say, what's 1.17 divided by the square root of 65, okay? And let's take a look. Y'all, I'm going to go ahead and go to two decimal places. What do you think, 0.14 or 0.15? 0.15, right? Very good. Oops, why did I write 14? 0.15. Excellent. Okay, so now, y'all, let's see if we can find that probability. Let's convert this to a z-score, okay? So look, y'all, our sample average, 22.6. We're going to write that right here, 22.6, minus our population average. Our population average, we said, was, what, 23? Divided by our new standard deviation for our sample means. And didn't we get that to be a 0.15? Okay, so look, y'all, let's take our calculator here. Let's go 22.6 minus 23, okay? And we're going to divide that by a 0.15, okay? Are y'all coming up with negative 2 point and a whole bunch of sixes? Okay, so guys, if we're going to go to two decimal places, what would I write? Negative 2.66 or 67? 67. Okay, so look, y'all, we're trying to find the probability that z is less than negative 2.67. I want you to think about my picture here. Remember, in our standard normal distribution, y'all, remember, this is 0, that's 1, that's 2, that's negative 1, that's negative 2. We are looking somewhere over here, negative 2.67. And y'all, how do I know that I'm going to the left? Look at my arrow. My arrow is pointing to the left, right? Okay, so y'all, this is what we did on Tuesday. This is what we did last Thursday, right? Okay, so look, my friends, we're going to go normal, CDF, right? CDF. What are we going to use if we're all the way out there to the left? Anybody remember? Negative 5,000. Awesome. Thank you so much. Where do we stop, y'all? Negative 2.67. Okay, so look, let's try that. Let me clear my calculator. Let's go second in VARs. Let's go to number 2 because we want to go to normal CDF, right? And we said, because we went all the way to the left, y'all, we're going towards negative infinity. And we said, hey, why don't we use something like negative 5,000? That's a pretty small negative number, right? And then we stopped at negative 2.67, okay? And boom, here we go. Okay, so y'all, if I'm going to go to 4 decimal places, what do you think? 0.0037 or 0038? 38. Very good, y'all. So our probability 0.0038. Okay. Y'all, remember what we talked about? And we said if we wanted to convert this to a percent, we would have to take our decimal place, move it 2 spaces to the right, right? So wouldn't we get something like 0.38%, right? 0.38%. Y'all, that's a pretty small percent. Okay. Now, let me tell you about what does it mean to be unusual or not, okay? Less than 5% is unusual. Okay. Less than 5% is unusual. I'm going to ask you guys a question. Is 0.38%, is that bigger or smaller than 5%? Smaller. Okay, so the sample mean, and guys, when you click on this thing, it's either going to say is or is not. And we're going to say it is because it has a probability that is bigger or smaller than 5%. What do you think? Was this number bigger or smaller? Smaller, right? So we would say, hey, look, that's going to be smaller, right? Now, y'all, had my percent been bigger than 5%, had it been 8%, had it been 17%, had it been 65%, doesn't matter. As long as it's bigger than 5, then we'd say it's not unusual. Why? Because it's bigger than 5%. Somebody, the last time I taught this, says, Omar, what happens if it's 5.1? That's bigger. Okay, as long as it's bigger than 5. Now, 5.1%, somebody could argue, well, that's still kind of unusual. Yeah, it's kind of unusual. But if we're going by this rule, like that's what the cutoff is, right? The cutoff is this. Remember, guys, next week is spring break, or the week after next is spring break. Anybody ever go to the stock show? I'm sorry? You're going next week, right? So guys, if you ever go to the stock show and there's usually a little sign that says you got to be this tall to ride the ride, right? And you're like, look, I'm almost there. They're going to tell you, sorry, man, I wish I could help you out, but next year, little man, right? And they'll let you in the next year, right? So there's a cutoff. So again, y'all, if it's 5.1%, 5.01%, not unusual, okay? So anything smaller than 5% is unusual. Y'all, let's try another problem similar, okay? And let's see if we can figure out what we got going on here. The mean annual salary for flight attendants is about $65,000. Okay, y'all, first thing I'm going to do, my average, $65,700. Okay. A random sample of 48 flight attendants. Okay, second thing I'm going to do, my N, my friends, is 48. Okay. What is the probability that a mean annual salary of a sample is less than $63,400? Okay, let's do this. We're trying to find that the probability that our average of our sample is smaller than $63,400. And if you notice, y'all, they gave us our standard deviation right here. Okay. Y'all, my first thing we're going to do, we are going to convert this to a z-score. Okay. This is my formula. Okay. So, y'all, my average of my samples is 63,400. Let's write that down. Minus, remember, y'all, my average of my population sample is the same one right here, $65,700. What we need to find first, y'all, is our standard deviation of our sample. Okay, let's do that. Let's do that right here. That's going to be sigma divided by the square root of n. Okay. So our sigma, y'all, they already told us that was $14,500 divided by the square root of n. What was my n number in this problem? Anybody know? 48. Excellent, y'all. Okay, so look, guys, I'm going to come back here. Let me turn this guy on. Let me clear everything out of here. Let's take $14,500. Boom. And let's divide this, y'all, by the square root of 48. And let's see what we get. Y'all, if I go to two decimal places, would you guys say 2,092.89 cents or 90 cents? What do you think? 89, right? Why 89? Because look at the number to the right of the 9, y'all. It's a 4. Remember, if it's a 4 or smaller, we leave it alone. But if it's a 5 or higher, we kick it up. So we're going to say $2,092.89. Okay, here we go. Y'all, that is a number that we're going to write right here. Okay. Let's do our calculation. 63,400 minus 65,700. Okay, it equals, let's divide that by 2,092. $92.89. And I'm coming up with negative 1.0989, all that kind of good, funky stuff. Guys, again, with our z-scores, we always go to two decimal places. What do you think? Negative 1.09, negative 1.10. What do y'all think? Somebody said it. 10, right? Very good. Negative 1.10. Okay, y'all, what we are trying to find, my friends, what's the probability that z is smaller than negative 1.10? Okay. Remember, you guys, the number here is 0. That's 1. That's 2. Here's negative 1. Here's negative 2. We're looking at negative 1.10. Aren't we going to the left again? And you say, how do I know I'm going to the left? Because that's the way my little arrow is pointing. Okay. So, sorry, guys, I should have left a little bit more space in here. Apologize. Let's go normal. CDF. Okay. Y'all remember what we said? If we went all the way to the left, where did we start again? Negative 5,000. Very good. Guys, sometimes people ask me, oh, Mark, what happens if I put negative 10,000? Doesn't matter, right? As long as it's a really small number going to the left, right? Would I put like negative 10? Probably not. I'd go way out there, okay? I'm sorry, where did we say we were going to stop at, y'all? Negative 1.10, okay? Let's try that, and let's see what we come up with. Let's go clear, second vars. Let's go to number 2, normal CDF. We said negative 5,000. There we go, comma, and a negative 1.10. Okay, boom. All right, so y'all, to 4 decimal places, what do you think? 0.1356 or 1357? 0.1357. And guys, I'm going to leave it like that. But if they ask me to write that as a percent, do you all agree it'd be 13.57%? Okay. Would that be unusual? No, because it's more than what? More than 5, right? Boom, there you go. Yo, before I go on, I want to just kind of come back and look at this question that we did, right? Remember what we said the average salary was for flight attendants? We said that the average salary for flight attendants was what? 65,700. And look at the standard deviation, 14,500. So what does that mean? We took all the flight attendants and we found all their average, we found all their salaries. We took their average of every single flight attendant and we found their standard deviation. So that means that if your salary is 65,700, the next chunk over would be another 14,500, and the next chunk over to the left would be subtracting that number, right? 14,500, that's a pretty big amount of money, right? But what we're saying now is that if we were to have taken 48 of them, the salary would still be 65,700, but the difference in them would only be about $2,100, right? If I rounded to the nearest hundred, like 2,100. So the next group over would be 2,100 more, and the group that's making a little bit less would be about 2,100 less. That, my friends, is the idea of the sample means. When we do our sample means, my average is the same, but the spread is a much tighter spread, okay? All righty. Let's see if we can figure out, y'all, next problem. And we'll go through very slowly and make sure that we're all good here. Okay, so y'all, it says from 1975 through 2020, the mean annual gain of the Dow Jones Industrial Average was 651. Okay, my friends, step number 1. My average, 651. Okay, a random sample of how many years? 35. That's my sample size, 35 years selected from the population. Okay, and then right here, y'all, it says, what is the probability that the mean gain from the sample was between 400 and 700? Assume a standard deviation of 14 or 1540. I'm sorry. Okay, so let's take a look at what they're asking me to do here. They're looking for the probability that our gain was between 400 and 700. Okay. The mean of that sample. So let's do this, y'all. We're going to have to find two z-scores, one for 400, one for 700. Before we do that, y'all, let's find the standard deviation of our sample size. So remember, we're going to take our standard deviation and we're going to divide it by the square root of n. So I'm going to take my calculator right here, 1540, and we're going to divide it by the square root of, what do we say our sample size was? 35, right? Boom, 35. Okay, let's take a look. Y'all, 260, 30 cents or 31? 31, very good. 260 and 31 cents. Again, hey, look, the average and the change in those 35 years, not as much as the overall change. Okay, let's do this, y'all. Let's find our two z-scores. Okay, z1, we're going to take our first x value, 400, minus our average, 651, and divide it by that. Okay, so 400 minus 651, oops, 651, and divided by 260.31. Okay, negative 0.96. All right, let's do our second one, y'all. Let's do our Z2. Let's take this guy, 700 minus 651 divided by that. Okay. So 700 minus 651, okay, and divided by 260 and 31 cents. And let's see, 0.18, 0.19. 0.19, very good, y'all. Okay, now what is it we're trying to find? That our probability, y'all, is between those two numbers, right? Okay, y'all, what I like about when we write it this way, you can see what your lower limit and your upper limit is already, right? We're going to go normal CDF. Let's go like this, second vars, oops, sorry. Second vars, normal CDF. We're going to start at a negative 0.96, and we're going to go to a 0.19, okay. All right, and let's hit enter. All right, so y'all, this is what I'm coming up with. What do you think, 0.40, 68 or 69? 68, right? So 0.40, 68. Okay, 0.40, 68. Now, y'all, I want you to notice something here. Look at my answers. They're asking me to write them in percents. How would we change this to a percent? Anybody know? We got to move our decimal point 2 spaces which way, left or right? Right. So wouldn't we say 40.68? Okay, so look, y'all, 40.68 have in how many years? How many years were we looking at here? 35. Okay, so look, y'all, if I look at choice A, it says 46. I know that's not going to be good. Okay, so my choices B, C, and D all have 35, right? But we're looking for those values between what two numbers? 400 and 700, right? So which one would I pick here, y'all? A or B, C, or D? C, right? And wouldn't we put 40.68, boom, right there? 35 samples between 400 and 700. Does that make sense? You got it, right? Is this similar to what we were doing the other day? Right? This one change, guys, the sigma part, right? That's the only small change that we really got, okay? So, y'all, I think I got 2 more questions for us to do, okay? Yeah, 2 more questions for us to do. Number 6, and yes, this last one over here, okay? So, number 6, it says the height of women ages 20 to 29 are normally distributed with a mean of 64.9 inches. Okay, so let's write out some things here. My average, 64.9. our standard deviation 2.7. Okay, it says, are you more likely to randomly select one woman with a height of less than 66.7 inches, or are you more likely to select a sample of 25 women where their average height is less than 66.7 inches? Okay, and it wants us to explain. So look, y'all, when we do the first part right here, what's the probability of selecting one woman that has a height less than 66? Okay, what I'm doing for part A, y'all, what's the probability that X is less than 66.7? Y'all, this is one person. We're not looking at a sample right now. We're doing what we did Thursday, what we did last, or Tuesday, what we did last Thursday. Okay, so the first thing I'm going to do, y'all, I'm going to convert this to a z-score. Okay, we're not looking at a sample right now. We're looking at one person. Okay, not a sample, not an average, not a group of people. We're looking at one person. Remember, my average or my X value here, y'all, 66.7 minus 64.9 divided by 2.7. Okay, let's do that. 66.7 minus, we said our average was 64.9. Okay, and we're going to divide that by 2.7. Oops, sorry. Come back, 7. Okay, and 0.67. Okay, so look, y'all, what we're trying to figure out is what is the probability that our z-score is smaller than 0.67, right? Yeah, 0.67. Okay, so remember, y'all, normal CDF, we're going to the left. If we're going to the left, our lower value to the left, y'all, should be our negative 5,000. 1, 2, 3, okay, comma, and then a 0.67. Okay, let's do this. And y'all, if I go to 4 decimal places, 0.7485 or 6? 6. Okay, 0.7486. All right. Now, what's the probability that we select a sample of 25 women who have a height less than this? Now we're talking about a sample, okay? So now we're talking about what we've been doing so far, okay? Let's do it like this, y'all. We're trying to find that the probability that the average height of a group of 25 women is smaller than 66.7, okay? Let's find our z value, okay? We're going to take x minus mu x over sigma x, okay? Remember, y'all, my average is still the same. That is still 64.9. So we're going to take 66.7 minus 64.9. Oh, don't we need to find this guy right here? Okay, let's find that guy right there. Boom. Remember, y'all, it's going to be the previous one, 2.7 divided by the square root of 25. Anybody know what the square root of 25 is anyway? It's 5, right? So let's do this, y'all. Let's take 2.7, right, divided by, we already know what the square root of 25 is. We know that's 5. Okay, 0.54. So that's my number that I'm going to put right here, okay? So let's go ahead and find those differences. Let's take 66.7 minus 64.9, hit enter, and let's divide it by the 0.54. And y'all, 3.33? Okay. Okay. Again, y'all, I'm going to write my answer here. We are going to the left. Remember, y'all, when we are going to the left, our lower value, negative 5,000, right? Boom. Or 50. And 3.33. And let's close that off. What do y'all think? 0.99, 3 nines and a 5 or a 6? Right? 0.99, 90, oops, sorry. 0.99, 96. Okay. So look, y'all, let's compare our two probabilities. Which one was bigger, the first one or the second one? What number is bigger, 0.7486 or 0.9996? This one here, right? Again, if you think about them in terms of percents, 74%, 99%, right? Obviously, this one is bigger. So the one that was bigger was the one where we selected a sample of 25 women, right? So look, y'all, we're going to say there's two of them. It's more likely to select a group of 25 women. Now we got to figure out which one says it has the higher probability. Look at choice B and look at choice D. Those are the ones we want, right? Because that had the higher probability. But which one says it has the higher probability? D, right? And you say, why is it D? Because look at B. B says it has a what kind of probability? Lower, right? And it didn't. That's why we wanted choice D. Okay. All right. So, y'all, I got one last question for us to do. I thought this was kind of a neat question, and especially for those of you who are going into the social sciences, whether you're going into sociology, whether you're going into psychology, or does anybody ever watch like Narcos? Anybody see Narcos? Did any of you guys ever see Griselda, the one with Sofia Vergara? Did y'all see that one? Y'all know what I'm talking about? Yeah. So she was a drug cartel, right? Leader, ringleader. But it's a woman. And social norms, when you think about drug cartel people, what do you normally think of? It's a man or a woman? Usually it's a man, right? So when you guys, if you've seen Griselda, if you've seen it, it's pretty like uh what I found it to be was kind of like eye-opening, because you did normally when you think of somebody who's very brutal, you typically think of men are going to be the more brutal ones, right? But if you watch Griselda, it's on Netflix. I mean, if you got time, check it out. Spring break's coming up, right? It's only like 6, 7 episodes, but it is done very well and ruthless, y'all. That's the word I would use to describe it. Yeah, yeah. She guys, this was like back. Okay, so y'all know a couple of months ago, former President Jimmy Carter passed away. Okay, Jimmy Carter was president, y'all, when I was like in kinder. So it was a long time ago, right? Long, long time ago. One of the things he did was he was trying to help the relations between the United States and Cuba, told Fidel Castro, we will welcome Cuban immigrants to come over. Fidel Castro decided, instead of me sending people who are just trying to get out of Cuba, he sent people who were in mental institutions. He sent people who were in prisons. That's who he sent to the United States, right? Because he was trying to be, create conflict, right? Um, a big in the show Griselda, a lot of those people went to go work for her, and she welcomed them in. And I mean, they were criminals, right? So you're going to work in a criminal organization already, right? But like Natalie, right? Yeah, sorry. Like Natalie said, they praised her. They were like, she's the padrona. She's the one, right? Okay, anyway, let's take a look here, y'all. It says an investigation of personality characteristics of drug dealers of a certain region, convicted drug dealers were scored on a scale that provides a quantitative measure of a person's level of need for approval and sensitivity to social situations. Higher scores indicate a greater need of approval. Based on the study results, it can be assumed that the scale scores for the population of convicted drug dealers has a mean of 36. Okay, I'm going to stop right here. My mean is 36. My standard deviation is 4. Okay. Now, let's take a look at the next part. And a sample of 103 people from the region. So look, y'all, my N is 103. It says that average was 37. Is this sample likely to have been selected from the population of convicted drug dealers? Explain. Okay, so y'all, I like this question. I actually pulled this question out of a different textbook. I like parts of this question, and there was other parts that I didn't like. And the part that I didn't like was, hold on, am I trying to find the probability that my score is bigger than 37 or less than 37. And it doesn't really tell me anything until I start to look at some of these things here. Okay. So let's do it this way. Let's find the probability that our score, and maybe what I'm looking for, guys, here is that greater need, right? Greater means it's going to be bigger than. Okay. So our score is going to be greater than 37. Okay. So y'all, let's do this. Let's find our Z value. Okay. Okay. So I'm going to zoom out a little bit here just so I got some more room to work. Let's see. Okay. Our X bar, y'all, is 37 minus our average, which was 36. But we need to find this number. Y'all agree it's going to be 4 divided by the square root of 103? Right? Because it's my previous one, my previous standard deviation, 4 divided by the square root of a 103. Okay. And y'all, I'm going to go to 2 decimal places. What, 0.39? Okay, 0.39. Okay. So let's see what we got. 1 divided by 0.39. 2.56. Is anybody else coming up with the same number? Okay, now y'all, I got a question for you. Here's my basic picture. 0, 1, 2. We are looking at, y'all, 2.56. And we are looking to the right. So if we're looking for the probability, and if we're looking at the probability that my Z value is going to be bigger than 256, right? We're going to go second bars. We're going to go normal CDF. Do y'all agree that my lower limit would be 2.56? Okay. And if we're going all the way to the right, what number do you think we're going to stop at? 5,000. Very good, right? Because we're going to the right. We're going bigger this time, right? So look, y'all, look at the number that we're coming up with, 0.0052. Okay. All right. So y'all, 0.0052. Look, they want me to go to 4 decimal places. Okay. So let me just write it right here so that we got our answer. Okay. Now I got to figure out, right, which one am I going to choose? Okay. No, because the probability of convicted samples is whatever my number is, which is less than 0.05. No, because my answer 0.0052 is greater than 0.05. Or yes, because my sample means, and we're doing greater, y'all, because we were talking about a greater need, right? Higher scores. So I can already eliminate this one here. Okay. So let me think. I want you to look at the 2 choices we got, y'all. We got choice A and we got choice C. Was our probability bigger or smaller than 0.05? When we came up with 0.0052, is this number bigger or smaller than 0.05? What do you think? Smaller, right? It's smaller. So y'all, we're going to put right here, oops, sorry. We're going to put 0.0052 because it is smaller than that. Now, I want you to look at the question. I want you to look at the first part of it. Does it seem that this person who scored, this group of people who had an average score of 37, could it have been possible that they were convicted drug felons? And we're saying no. Now, remember what we said, y'all. The higher the score that you get, right? Look what it says right here, y'all. Let me just kind of clean this up. Let's see. Here we go. They measure a person's need for approval and sensitivity to social situations. Higher scores indicate a greater need for approval. Now, we're talking about convicted drug dealers. Y'all, I'm not talking about your cousin who says, hey, man, I got a bag of weed. You want to buy it? I'm not talking about that dude, right? I'm not talking about that. I'm talking about people who sell heroin to 11-year-olds, right? I'm talking about people who will pimp and prostitute people out just to make some money. Do you think that they have a need for approval from anybody else? Do you think that they are sensitive to social situations? No, right? They're not, right? So again, y'all, those of you going into the social sciences, right? Why are we getting such a low probability? Because those people, their minds, right, are work in a different manner, right? I don't know about you guys, but I don't think most of us, right, say, hey, I know I made the joke the other day, hey, you want to buy some crack, right? But I know that we're not out there, y'all, going to elementary school kids or junior high kids or anybody, right? And saying, hey, you want to try this fentanyl, see what it's good. We're not doing that kind of stuff. Anyway, my point, y'all, when I saw this question, I thought it was kind of neat because it brings out, right? It shows mathematically everything that we've seen on TV, whether you're going old school and you're watching Scarface with Al Pacino or something like that, or you're watching Narcos or whatever, anything like that, you can see, right? Their personalities, very different types of folks. Okay. Y'all, let me ask you a question. Scale of 1 to 10. 1 being like, sir, this was really hard. 10 being like, hey, that's easy breeze to cover, girl. How do you guys feel about what we did today? Anybody got a number you want to throw out there? A 3, a 7, 7? Okay, good, y'all. So, again, the idea, I want to make sure that you guys feel pretty good as we go through it. And I want you to notice that my process with every problem, y'all, was the same, right? The only thing that we changed today, y'all, was that little standard deviation, right? My average still did the same thing. How did I find my Z-scores? The same way we found our Z-scores before, okay? Yo, let me do this. Let me stop recording. So let me come back over here. Boom, let's stop recording.